Hey yo, ever wonder how computers move data at the lowest level? The move command is at the heart of assembly language, yet it often confuses beginners. In this video, we are diving deep into how move works in x86 assembly, examining byte order, using NASM to compile, linking with LD, and stepping through execution with GDB. Whether you are new to assembly or just want a clearer understanding, this is the video for you. We'll walk through a real assembly file, compile it with NASM, debug it in GDB, and watch memory changes in real time. By the end of this, you'll understand not just how move works, but why byte order matters and how to analyze assembly like a pro. If you are into low-level programming, debugging, or just love getting hands on computer internals, stick around. This will be fun. I've created a little program to demonstrate these couple move instructions. There is a data section. Here we have an address test with a double quote minus with a value of -1, which will end up all FF in that 64-bit address, which is the complement of the -1 value. The program is just a couple demonstration of how to use the move instruction. The first one, line 9, we move the immediate value 0x12 into the address, but specifying the data type is a byte, which means to give an instruction that says the width of the slot is a byte, which is 8 bits. That just means don't touch the things that's outside of that slot, only 8 bits. And the next one is we move the value in immediate value 0x1234 into the slot, but the width is a word, which is 2 bytes. That's 16 bits. This correspondingly is a double words. The immediate value is 1, 2, 3, 4, 5, 6, 7, 8. Double word means 2 words, which means 32 bits, 4 bytes. And this is 64-bit one. We can see that we can't write the 64 bits immediate value into the code because of the limitation of the 86-64 assembly language. So that just means we can only specify 32 bits maximum. But because if we need to write a quad word, both in lower 32-bit and higher 32-bit, this won't work because this only will just write to the lower 32 bits. And then this is the exit. We'll see how it works. We build I created build script. We can have a look, see what it does. It's simply just call the NASM to compile the ASM file into object file by specifying the format is ELF64. ELF is executable and linkable format. -G is to enable the debug information, and -F dwarf is specifying the debug file format. Dwarf stands for debuggable with attributed what is R? I couldn't remember. Debugging with attributed record formats. After compile to an object file, we'll run the LD command to link the object file into the executable ELF file. That's pretty simple. Build and then move. So we compiled successfully. Now I'm going to use the GDB to step through the program to learn how these instructions will behave. Move and then text user interface, specifying text user interface. We switch the layout to ASM, so when we run the program, it will display the disassembled language codes. There's a command called start I. It will just run the program and stop right at the first instruction. I noticed that by default, the text user interface is focused. You can see that there's a cyan border around the user interface. That just means if I use the scroll, if I use the up and down keyboard, it will scroll the disassembled code. I don't need that. I want to move the focus away from that text user interface, so I can use the up and down arrow to show the command that I typed in before, to just go through the history, similar to Linux terminal. So what I do is Control X and O, so it's now the focus is on the GDB command line. So when I press up and down, it will just go through the command history. So we can see the first instruction is to move immediate value 0x12 into the address 0x402000. So before I run this command, I'm going to check what's inside that address. We can do this by typing X and the number of data, like 8. I want to display 8 bytes. And we also need to specify what kind of format we want to display. So I'm going to show it as hexadecimal, X, and 8 bytes. And then specify the address. So you can see they're all 0xFF, which is the representation of -1 in complement format. Now I can run this command to move byte. You can see it's executed, and we can see what's at that address. So we clearly can see that the 402000 becomes 0x12, so the move a byte into that address is a success. So let's move to another instruction. Then we check the address again. It becomes 0x34, 0x12. The reason it's not 0x12, 0x34 is because the memory address is using the Little-Endian byte order convention. Little-Endian byte order convention, it simply just means the least significant byte goes to the lower memory address. Because in the immediate value 1234, 12 is more significant, right? Because it's higher. 34 is least significant, so that's why it ends up in memory layout becomes 0x34 and 0x12. So let's move on to the next one, double words, and then see what's changed. So we can see that 4 bytes becomes 0x7A, 56, 34, and 12. So that's exactly a reverse order of the original immediate value 1, 2, 3, 4, 5, 6, 7, 8 in a double word width, which is 32 bits, 4 bytes, and 2 words. Okay, next one is the quad word, which is 64-bit. But as I said, because of limitation, we can't write that or 64-bit information as an immediate value into the code. So what we expect is it should be like this, in reverse order. But we can clearly see that the higher 4 bytes, the higher 32 bits all clear out. It becomes 0, because in the intermediate value is only set the lower value, and the upper 32 bits will be 0. So it move all 0 into the address from 40 to 1004 to 7 to 7. Yes. Okay, that's it. It's all working properly and as expected, and I think I have explained this clearly, and I've learned something, which is awesome. I hope you also learned something. See you next time. Cheers.